A very good morning to all of you, and uh, in continuation to the last talk that we have been talking about, we are trying to touch some of the important points uh, and trying to take all of those points in a very philosophical sense. And today I'll be talking about the Big Bang. I'll be talking uh, about the origin of the universe. And to begin with my talk, uh, it becomes essential that you have to come up with an argument that can work. So science works based on two things. One is the argument, the postulate. The other thing is confirming that postulate, which is mathematically predicted in a laboratory where we perform those experiments. And when we stand to try to understand what could have been the possible starting point, whether there would have been a starting point or not, that's another important question. But there happens to have the experimental evidences that let us understand, at least from experimental point of view, that what could be the plausible ways that we can introspect to come up with an argument that why there is a universe. And the point seems to be that if we go with the argument of the Big Bang, which is the highly accepted theory based on the support that it has got from experiments, we have to start with a point, what we call as singularity. And this singularity is comprised of the all energy that we have in universe today, the all matter that is born out of that energy in the universe, in the observable universe today, and the space. That means there was no space. This singularity carried space, it carried energy. And it takes as the starting point. So there was no time. The time that we understand, the time starts just at the point this singularity has an explosion. Now, how could we analyze, how could we think about that singularity being there, having all the information inside that singularity? And it's not something like that you have a singularity somewhere in this space. There is no space at all. You have a starting point, and you call this starting point as the singularity, comprising of the energy, start of the time, and all that matter that exists in the observable universe today is the result of this singularity. And this singularity, if it has to be consistent with second law of thermodynamics, it has to have all the order. Everything that this singularity possesses has an order. And it's the order of what happens in terms of the disorder. So it's the order that leads the universe from one point to another point, from one state to another state. So here we have to assume that if we assume that there used to have, there was a singularity, we have to assume this reality that this singularity was containing all that order. And this order is continuously transforming into the disorder. So you have a Big Bang, and this Big Bang leads to the disorder in the universe. And universe is extremely mysterious. And this is a photograph showing us the observable universe, the universe that we can detect using all sort of technologies in terms of telescopes. And it is impossible for us to reach beyond the boundaries of this observable universe. Now, what I want to start with is that singularity. And there are a number of theories that are proposed for explaining the origin of the universe. And the Big Bang theory is the highly acceptable theory because it's purely supported by the experimental observations. And so there had a bang kind of thing, and this bang happened nearly 13.8 billion years ago. And at this bang, there was a rapid expansion. The expansion was like this expansion was accelerating with the speed greater than that of the speed of the light. And to support this bang, we have the two important theories in astrophysics. And these theories are, the first one is the cosmic microwave background, what's called CMBR, and the another important one that is the redshift that was observed in galaxies by Edwin Hubble. So these are the two basic experimental evidences, experimental parameters that support that there could have been a singularity comprised of all energy and time, and it's this singularity that has undergone a rapid expansion. And this rapid expansion is called as the inflation of the universe. Now, as he talked about the redshift, so what Edwin Hubble observed while observing the universe, he could find that most of the galaxies surrounding the planet, they are moving away from each other. And finding out an argument that their acceleration is proportional to the distance with respect to which these galaxies are moving away. Now, if an object is moving towards the planet, then we may call it a blue shift. And if it is moving away from the planet Earth, we will call it the red shift. So what Edwin Hubble observed, he observed that most of the galaxies in the universe, in the observable surroundings of the planet, are moving away. They're moving away from each other. And they are not only moving with some some range of accelerations. They are accelerating with the speeds greater than that of the speed of light. So this is what is called redshift, and it has its basis in one of the basic principles of classical physics, what's called as Doppler effect. And the second important experimental support of the Big Bang theory comes from CMBR, what we call as cosmic microwave background. So as I was talking about the inflation, as I was talking about the rapid expansion of the universe, and this expansion has given birth to some kind of signal falling into the microwave range of wavelengths. And the discovery of the cosmic microwave background was another important experimental support for the singularity being the starting point of the universe and leading to something called as the Big Bang. And there could be some other plausible arguments about the universe. So there has been a state of evolutionary stages that can be accumulated stepwise for the expansion of the universe, starting from a singularity. And what is predicted is that in the very first between first 10 seconds, if we take this starting point as 10 seconds, it was possible for neutrons and protons to come into the existence. And this existence of neutrons and protons, it laid out there up to a long range of time, and that time falls in the category of 380,000 years. Now you have a Big Bang, and this Big Bang gives birth to these subatomic particles like neutrons and protons, and the neutrons and protons, they cool down. The atmosphere of the universe cools down to a state that these neutrons and protons, these particles, they combine and they are able to form the simplest form of atoms. And these atoms are mostly what we call as hydrogen atoms and helium atoms. And then from 380,000 years to nearly 300 years, we call this zone as the dark age of the universe. And in this age, the universe cooled down. It cooled down to an extent that they laid down the foundation. They laid down the foundation for the formation of stars. And once the universe crossed 300 million years, there was formation of stars. And there was formation of galaxies. And in this era, what happened is most of the stars that were formed in this era, they underwent supernova. And what is supernova? Supernova is the explosion, and since these stars the star formation was based on the gravitational clustering. It was the gravity that was responsible for attracting these atoms of hydrogen and helium, and they could come together and fall into and form a star. And once a star is formed, there would have been the possibility of forming the higher order elements. Other than that of hydrogen and helium, the elements like iron, the elements like nickel, cobalt. So all of these elements could be produced during those nuclear fusions that have led to the formation of these stars. But what happened to these stars is they underwent supernova, and once they went into supernova, there was a lot of stuff available in the universe. The stuff, what's generally called as the dust, and this dust is comprised of a long range of matter in the universe. And then once this age of 300 million years to 1 billion years is past, we fall into a domain of the formation of early galaxies. So there is formation of galaxies, and these galaxies are formed by virtue of the gravitational contraction of the matter that was available in the universe. So it was the gravity that led the formation of galaxies. It was the gravity that led to the formation of different geometries of these galaxies, like spiral galaxy. And if we move on from here and we go back to 4.6 billion years, our solar system was created. And this solar system would have come into existence only because of the debris that would have been present in the space by virtue of some kind of supernova that would have already taken place in the space. And to support that fact, when we see around the solar system, which has come to existence 9 billion years from the starting point, we encounter the meteorites, we encounter the bodies that are present in the solar system, and the matter, the composition of the matter in those galaxies, in those meteors, is homogeneous. It's same. It has everything to do with the formation of the planets in our solar system. So this is a short story, as I have talked about the Big Bang, supporting that there would have been a singularity that has led to the formation of all the galaxies, stars, black holes, quasars, all of those things that are there in the observable universe, supporting the fact that everything has started from a point, what's called as singularity. But at the same time, I would like to go into the other models of the universe, and there is a model what's called as steady state model, and it is an alternative model. It does not believe in a bang, and it does not have any singularity with which it can start its models. And what this steady state theory tells us, it proposes that universe is eternal, it's unchanging in density, and matter is continuously created as the universe expands. So there has to have a perfect cosmological principle. So whatever there is, that was there, and that is there, and since what we observe is that the universe is expanding, it's expanding to compensate that expansion. The there is continuous creation of the matter in this steady state universe. It is eternal and infinite universe. It has no beginning, and it's not going to end at some point in the future. But as I started with the two important arguments, the argument of redshift, maybe that supports, because there is a model in this model that says, come on, the expansion is compensated because of the formation of the matter. But if we take both the theories, cosmic microwave background and redshift, they are completely rejecting the steady state universe. And this model itself is trying to reject the postulates, the arguments of the Big Bang theory. And there certainly are challenges. As I said, it fails at CMBR, and it does not fit to accurately explain the experimental outcome that we have available in the laboratories. It doesn't go with that. It doesn't go well with that. Then there is another way of thinking about the origin of the universe as an infinite kind of thing happening, what's called as oscillating universe theory. It's a cyclic kind of model that what you have, the universe is created and then it goes and then it comes back to its initial state. Then again it goes and it comes back to the initial state. Like an oscillating pendulum that we have, treating a universe infinitely going on from a starting point to an end point, being the end point being the start of the next event. So in this oscillating universe, what we have, it's a cyclic model, and big bangs are followed by a big crunch. So there is a big bang, then there's a crunch. Then there's a bang and there's a crunch. And what does that mean? That means universe expands, it contracts, and repeats after every interval of time. And certainly it has challenges because the theory cannot, there is no experimental evidence that can support the argument of the big crunch. Because if we go back to Edwin Hubble, the predictions, the observations of Edwin Hubble, these observations are telling us that the universe is expanding. So there's no direction in the universe where we can see even a fraction of the argument that's given by oscillating universe theory, because we are not observing any kind of contraction. So this oscillating theory has challenges. But I would like to tell, I would like to make an argument here that the theories like steady state theory or the oscillating theory, they are doing their job, and they are the job they are doing in formulating a better theory for the existence of the universe. So they are actually playing a role to the mankind, so that we can have more in-depth understanding of the universe. So this is what I was telling. This oscillating universe is cyclic in nature. It has a resolution to some temporal infinity, and there are challenges in energy conservation. There are challenges when you treat this problem in terms of second law of thermodynamics. And there are two dependencies that are involved in oscillating theory of the universe. That's gravity and the density. So if you want the contraction, then the density should exceed, and if you want the expansion, then the density should decrease. So what we have is it has a conflict with entropy laws. And critics of these oscillating models point to the second law of thermodynamics, as I was talking about, which implies increasing entropy in each cycle. And this would certainly make this would make successive cycles progressively different. They are contradicting the idea of what we call as perpetual repeating universe. And as I said, that oscillating model has historical and conceptual importance, but modern cosmology largely favors the Big Bang theory, because for Big Bang theory we have repeated experimental evidences that are supporting that universe might have started from a singularity, carrying all information in terms of matter and energy and the space. And this is what I was talking about, an oscillating universe, a universe creating and then contracting and then creating and then contracting and so on. So we have talked about the inadequacy of steady state universe and the inadequacy of the oscillating universe. In fact, there are other theories that are out there having their own arguments about the existence of universe, the origin of universe, the universe that we have, and the universe that we have had, and the universe that we will have in the future. And there is another theory, what we call as multiverse theory. And multiverse theory is its origins can be thought in the domain of the quantum mechanics. And when we think in the framework of quantum mechanics, we can have some parallel realities going on. I mean, if we have a particle in a box and we calculate the probabilities that this particle can be in that one-dimensional box, so this particle can be at many places at the same point of time. So there is some philosophical argument coming from quantum mechanics that tells us that at least the theory is predicting it in a way that there can be some parallel realities going on, and one reality cannot intervene with another reality, and this is how quantum mechanics has an argument for multiverse. And even though if we go into the domain of quantum mechanics, and if we see nowadays we are moving towards a scientific age where we are trying to build a quantum computer, and quantum computer has it works on the principle where your reality can be multiple. I mean, you can have an action that can take many paths at the same point, and that is something that supports the theory of multiverse. Another important thing is cosmic inflation, and cosmic inflation. What it tells us that once there is a Big Bang, and this Big Bang could have given birth to a range of universes, and not necessarily the laws of physics would have been same for all the bubbles that would have formed at the time of inflation. And the inflation theory tells us that there could be a possibility where different bubbles generated with different set of laws of physics, and they would have given birth to the different universes. But the problem with the cosmic inflation theory is that it cannot be tested. It cannot be tested, but what we can test is the quantum mechanical interpretation of the multiverse. So I think I'll stop here.